Hello and welcome. In this video, I'm going to give a brief conceptual introduction to exploratory factor analysis, which is a statistical procedure that is used to summarize a set of variables in an attempt to find the number of underlying dimensions that are present in the data set or in the variables. So it's a often referred to as a data reduction technique and a descriptive technique that is used to identify the number of dimensions, factors, or latent variables. We can use those terms interchangeably present in a larger set of variables. So essentially the question or the goal of a factor analysis is fairly straightforward. It's let's see how many factors or dimensions can adequately summarize this larger set of observed variables. Unfortunately, the mathematics and the analysis is much more complex than the actual questions we're usually trying to ask or answer with a factor analysis. But in this brief video, I'm just going to go over the conceptual basics. To really dig deep into factor analysis, you'd want to brush up on the matrix algebra that underlies much of what we're going to be talking about. So, what do I mean by factors or dimensions? You've likely encountered at some point the big five personality variables. That's an example of a set of factors that were derived, at least in part, through factor analytic procedures. So for the big five personality variables, the responses to the items, usually the self-report responses to the items, those could be thought of as observed variables, and the factors themselves, the big five, neuroticism, openness, extroversion, and the like, those can be thought of as the latent variables that are presumably driving one's responses to the items that are on the personality inventories. So factor analysis, another way to put it, is used to identify variables that hang together or belong together or basically correlate with each other to form a factor, but don't correlate with or don't correlate relatively strongly with items that form other factors. So we want to find clusters of items that belong together and correlate with each other relatively strongly, but don't correlate very strongly with items that form other factors. There are two major types of factor analysis. One is exploratory factor analysis, which we're talking about in this lecture. Exploratory factor analysis is generally a descriptive technique that's used to identify potential factors among variables, but the researcher or data analyst may not have a very strong theoretical or empirical basis for asserting how many factors there are or the structure of those factors. So the goal in exploratory factor analysis is to identify, whereas in confirmatory factor analysis, it's used to test a hypothesis that should be based on previous theory or a previous empirical basis, or maybe even a previous exploratory factor analysis. It's used to confirm and test the hypothesis about how many factors there are, or compare different models with let's say a three-factor solution and a four-factor solution, and the structure of those models, where some might have a hierarchical structure and some may not. So a confirmatory factor analysis is a bit more complex, so we'll save that for another day. There's two major type estimation methods. There are actually many more, but the two I should say the two you're most likely to encounter are principal factors or principal axis factoring, which is a procedure that's used to identify the factors by first finding the factor that explains the most variance and then finding the next strongest factor and so on. This method is probably the most commonly used. It tends to have fewer assumptions than other methods, and it's probably the most well understood of the methods that exist in terms of like conveying your results. Now, maximum likelihood estimation is another fairly commonly used procedure that estimates the parameters, the factor loadings, uh, uh, in a manner that attempts to determine the population parameters that will be most likely to result in the data that you have in your sample. So this has the assumption of multivariate normality, which makes it, a little bit more uh, restrictive, but not terribly so. But the added benefit is that it allows one to have more fit indices. So if you want to compare different models, such as a two-factor solution versus a three-factor solution, you can use those fit indices to do that. Also allows for significance testing and confidence intervals, which the principal axis factoring method does not allow for. So those are the two that you're most likely to encounter. There's a handful of others that are less commonly used. So here I created a bogus data set with only 6 variables, which usually is not the best for factor analysis, because if you're trying to do an exploratory factor analysis, ideally you want a lot of variables that could potentially represent a sample of variables that measure the underlying factors you're trying to get at, and you would want also a large sample. In this fictional data set, I have neither of those things, but I think it'll be useful to just use a small number of variables as a instructional aid. So we can see here in this data set we have 3 variables that, let's say, presumably measure satisfaction with life from an economic perspective, and we have 3 variables that presumably measure satisfaction with life from a relationship perspective. And we can see that the economics items correlate very strongly or relatively strongly with each other. The relationship items correlate very strongly with each other, and the economic and relationship items, their correlations between them are fairly weak and around 0. So this, as you can tell, is kind of set up to have these 2 factors, but here we can get an idea of how items might cluster together or hang together to form different dimensions of a data set. So here, presumably, there's an economic satisfaction with life variable and a relationship satisfaction with life variable. An incredibly important statistic for exploratory factor analysis are the factor loadings themselves. So I conducted a factor analysis with the 6 items, and I didn't constrain it to have fewer than the maximum number of factors. So there's 6 items, so the maximum number of factors would be 6. Of course, that wouldn't be very good for summarizing the variables, but to initially inspect the factor loadings, I left it at 6 factors. So it looks like the first factor, the loadings, which represent the relationship between the variable and the factor itself, we can see the first factor has strong loadings, very strong loadings from the relationship variables. The second factor has very strong loadings for 2 of the economic variables, and a a weaker but probably strong enough to retain loading from the third economics variable. We see there is a third factor that has a strong loading from the third economics variable. So it's kind of suggesting that maybe the third economics variable uh, might belong on its own factor, but we have the economics 2 loading on that. So it's not as simple as the correlation matrix led us to believe, but we'll reserve judgment now for how many factors there should be. Certainly, if there were going to be 3 factors, we would want more than 6 variables. You usually want, a larger number of variables per factor, where 3 might be the absolute, minimum with some rare exceptions. Certainly, you don't want a factor with only one item. Ideally, what you want is a simple structure where each factor relates strongly to the items that belong in that factor. Or in other words, each observed variable correlates well with one of the factors, but does not correlate well with the other factors. So for example, Econ 1 has a simple structure where it correlates strongly with factor 2, but it doesn't correlate strongly with any other factors. Econ 2, on the other hand, correlates strongly with factor 2, but it also has a moderately strong loading on factor 3, and Econ 3 has a moderate loading on factor 2 and a somewhat stronger loading on factor 3, or actually a much stronger loading on factor 3. So that's Econ 3 has more of a complex structure, whereas the other items appear to have a simple structure, which is usually what is desired. So here we see the loadings of each observed variable on each factor, and then we can also see the amount of variance that is not related to a given factor in each item. So we can see item 1, it's 0.22. We've accounted for a remarkable amount of variability in Econ 2. Econ 3, not so much. Relationship 1, 0.34 has not been accounted for. Relationship 2 is basically entirely accounted for, and relationship 3 as well is mostly accounted for. So another important statistic in factor analysis is communality. Communality is the proportion of each observed variable's variance that is explained by the factors. So how much of each observed variable is explained by the factors collectively. And this can be calculated by squaring the factor loadings. So if you squared the factor loadings across a row, that is how you could, if you wanted to verify it, that is how you could determine the communality estimate. In output for a exploratory factor analysis, there will be initial communalities, and these are usually based on the r-squared value from a regression using all the other items to predict each item successively. And then the extracted communalities based on the factor analysis are the proportion of explained variance in each item by the factors that are retained. So the factors that you actually hold on to and keep. Another important statistic in factor analysis are eigenvalues. So the mathematics behind eigenvalues is actually fairly complex and requires matrix algebra. But from the output, you can determine the eigenvalues if they're not given in the output by simply summing the squared factor loadings within a column for the factor. So going back to the factor loadings, if you squared each of these and then summed them up, that would give you the eigenvalue for factor 1, and then you could do the same for factor 2, and so on and so forth to get the eigenvalues. So the eigenvalues are a way of determining how much variance a factor is explaining in the data set. So if you divide a factor's eigenvalue by the number of observed variables, it gives the proportion of the total variance that is explained by the factor. So what you'll see is the first factor will explain the largest amount of variance, and then each successive factor will explain less, because there's less left over, and the estimation methods are such that the first typically explains the most. So another important thing to inspect, probably one of the most important things to inspect in a factor analysis, is a scree plot. A scree plot is going to give you a good idea of how many factors that are actually useful and how many factors are not garbage in your data set. So here we have a scree plot. This is not from the data we've been talking about. This is just a picture of a scree plot. But here we see these factors here, the ones that have low eigenvalues and are kind of like at the bottom here, are garbage. Like they're essentially nothing factors. They're just garbage. Whereas this one is clearly accounting for a large amount of variance. This one probably is also garbage. It's certainly closer to the garbage than to being meaningful. So looking at this, one way to determine the number of factors visually is by inspecting the scree plot and looking for the elbow or the point of inflection that would tell you how many factors to retain. So looking at this looks like a one-factor solution. However, another criterion that has been used often, although it's not the best, is to retain factors with eigenvalues over 1. So if you use that criterion here, you would retain 2 factors. Now, the number of factors to retain is going to be primarily based on the eigenvalues, but you also have to look at the factor loadings themselves to determine, well, what is the meaning of the factors. So if this factor, if you read the variables or you interpreted the meaning of the variables that formed it, and you used that to form a definition of the factor and a label for the factor, you would obviously retain this one. Now, if this one turned out to just be a few items that were reverse coded and for some reason correlated with each other due to that methodological issue, then you would not retain the factor. So you don't want to just simply go off the eigenvalues to determine how many factors you would retain. You would also want to look at the factor loadings to attempt to interpret the meaning of the factors themselves. So a better approach to determine how many factors to retain is to do something called a parallel analysis. So what a parallel analysis will do is it will create a simulated data set, or actually it'll simulate a large number of data sets with the same number of participants or respondents or cases and the same number of variables. So just randomly generated garbage data, and then it will plot the eigenvalues or give you the eigenvalues. And here this will give the 95th percentile rank for those eigenvalues. So basically the higher end of the eigenvalues that resulted from the garbage data, the randomly generated data. So using this method, you would retain the, so here with the triangles and the dashes, that's the simulated data, the randomly generated data. So obviously we don't want to retain any of the factors that are below that, because that's telling us that those factors are worse than the randomly generated garbage data. We would want to retain the factors that are above the 95th percentile for our randomly generated data. So in this data set, we're likely going to want to retain 2 factors. Now we would have to still go back to the factor loadings to make sure that those factors make sense to retain. And usually there can be a bit of an iterative procedure where you might look at the factors, and let's say you find a complex factor, you would want to delete that factor, or complex observed variable, I should say, or you find a variable that doesn't load on any of the factors, you may need to clean up your data set and then rerun the analysis and determine how many factors you would want to retain. So once you determine the number of factors that you want to hold on to retain, I should say, it's often desirable to rotate the axes. You don't literally have to do this. The computer does this for you. When there's only one factor, so when there's a one factor solution, it doesn't make sense to do this. But when there's more than one factor, the factor loadings will become more interpretable if rotation is used. Now there are various types of rotation which are typically grouped under orthogonal. So orthogonal are when you don't want the factors to be correlated or the factors are not correlated, and oblique is when the factors are related to each other. So in an orthogonal solution, the axes of the factors intersect at 90 degrees, whereas oblique solutions, the axes of the factors intersect at different degrees depending on the factor correlations. And there are various subtypes within orthogonal and oblique. Orthogonal is the most straightforward to interpret usually, but many books on factor analysis recommend using oblique, and then if the factors are not correlated, then you could go to an orthogonal solution for simplicity, or basically an oblique solution would reduce to an orthogonal solution if the factors are not correlated. But I'm basically glossing over a lot here because there are various subtypes within orthogonal and oblique. Probably the default, if you're going with orthogonal, is for assuming that your factors are not correlated, is to use Varimax rotation. All right. Another piece of output that's worth noting is the reproduced and residual correlation matrices. So you have your actual correlation matrix, which is the relationships between the variables that you're entering into the factor analysis, but you also have a correlation matrix that is reproduced based on the results of the factor analysis itself, the factor loadings. So let's say you ran the factor analysis and you decided to retain 2 factors, as it looks like we should do based on this parallel analysis. So we retain the 2 factors, and then if those 2 factors do a good job of summarizing the data set, our reproduced correlation matrix, the one that's based on the factor loadings, that's computed based on the factor loadings, that correlation matrix will be reasonably similar and quite close to the actual correlation matrix, which would mean we did a pretty good job summarizing the data set using a smaller number of dimensions. So a good model will reproduce the correlation, the observed correlation matrix using the reproduced correlation matrix. The residual correlation matrix is actually there's not even correlations in that matrix. It's just simply the difference between the observed and the reproduced variables. So ideally the differences are quite minimal. So a basic overview of the steps for conducting an exploratory factor analysis, and I'll upload a video of how to conduct an exploratory factor analysis at a later time, but for now I'll just go over the bare bones basics of it. Is that first you would probably conduct the factor analysis with the maximum number of factors, which means like however many observed variables you have, and you would likely not even use rotation. You might even use something called principal components analysis, which I'm not going to get into at the moment, but it's a a form of analysis that's very similar to factor analysis, except it analyzes um, data the data in a way where all the variance is analyzed, whereas factor analysis analyzes it in a way that only the shared variance is analyzed. So factor analysis is more in line with the common factor model, whereas principal components analysis includes all the variance in the analysis, regardless of if it's shared with other variables or not. But in any case, you would start off with kind of a model where you have all of the, you don't constrain it to a number of factors, is what I mean to say. And then you would inspect the correlations, you would inspect the eigenvalues, and determine how many factors and the potential meaning of those factors um, that you're likely to retain. So you should probably use parallel analysis to determine the number of factors you want to retain. You can inspect the loadings for the tentative meanings. Of course, the rotation should help to determine the meanings more decisively. And then you would rerun it and specify the number of retained factors. So say your parallel analysis indicates that there's 2 factors. You can specify, okay, run the factor analysis now with only 2 factors. And then you'll get your results, and the garbage factors will be lopped off. And then you will inspect the factor loadings from the rotated method to determine the meaning. So the meaning of the factors has to be determined by the data analyst by consulting the variables or items that load on that factor. So there is some subjectivity involved in this, and then there's no, guaranteed solution, or there's no guarantee that the solution will make sense. So hopefully it does. It's possible that you just have a bunch of garbage data and there's not really underlying dimensions in your data, but hopefully that's not the case if you've set out to do a factor analytic study. And then, of course, you'll want to inspect the residuals to make sure that your reproduced correlation matrix closely matches the actual correlation matrix, and you'll if you've done maximum likelihood, want to inspect the fit indices to determine if the model that you've retained is reasonably well fit to the data. So many fit indices will compare the simplified model that you've retained rather, to the saturated model where you have the maximum number of factors. And if your simpler model fits the data almost as well as the more complex model, then that would indicate that you would want to keep the simpler model. All right, well, hopefully that brief overview has clarified a few of these statistics relevant to factor analysis. I'll also upload in the near future a tutorial on conducting factor analysis to further elucidate this somewhat complex statistical technique. All right, thank you for listening, and I hope you enjoyed that as much as I did.